In this video, we look at hypothesis testing for a proportion. So the idea here is we're looking at the proportion or percentage of a population that has a particular characteristic. And so we have the same 5 basic steps that we have in hypothesis testing with means. We're going to start with our null and alternative hypothesis. So we're going to have HO and H1. And so here these will be statements about a population proportion. We will then calculate a test statistic. So again, this comes from our sample data. And notice we will use p hat, the sample proportion. So the proportion in our sample that had a particular characteristic. And we will compare that to p, the value in the null hypothesis on a proportion test. And so just like with means, if we get z values or t values close to the center of the distribution, that tends to tell us that the sample data tends to agree with the claim or the null hypothesis. And so we generally fail to reject H0. But as that sample proportion gets much different from the proportion in the null hypothesis, this z value will get bigger and bigger, further from 0, and go out into the tails on that z distribution. So again, a z value way out in the tails leads us to reject H0 because the data tends to contradict the claim in the null hypothesis. So again, we will then calculate a p-value. We'll take this test statistic, go look it up in the z value in the z table, and find a probability. Based on this p-value, we'll either reject or fail to reject, and then interpret our conclusion in the context of the problem. So this is a proportion test. Same basic 5 steps as all our other hypothesis tests. Now notice here, this is based on a binomial distribution. So we take a random sample and count the number of successes or whatever characteristic we're interested in. And so the test statistic is based on this p hat value, our sample proportion. With means, remember, large sample meant n is 30 or more roughly. With proportions, remember, it's roughly np greater than 5 and nq greater than 5, because then this test statistic is well approximated by a normal distribution. So if we look at an example, here we look at an example involving arthritis, painful inflammation of the joints. And particularly here we're looking at pain relievers and looking at these side effects of pain relievers. So we decide if more than 4% of users of this particular pain medication suffer side effects, the FDA is going to put stronger warning labels on the pain medication. So we do a sample, or we conduct a research project here. So we sampled 390 patients and found 31 had side effects for this particular pain medication. So should the FDA put stronger warning labels on this particular medication? So here that 4% is sort of the cutoff or the critical value. The FDA is going to put stronger warning labels if more than 4% suffer side effects. So our alternative, or our research hypothesis here, needs to be p greater than 0.04. Second step, we plug into our test statistic. So we take p hat, 31 out of 90, our sample proportion, minus the 0.04 from the null hypothesis, all over p times q over n. If we plug that in, we get 3.98. So when you go look this in the table, it's off the table. If you think about it, our standard normal table goes from plus or minus 3.49. This is at 3.98, so it's way out in the tail. So the probability of being bigger than this is almost 0, or approximately 0. Very unlikely that we're that far out into the tails. So this is a very small p-value. Remember, small p-values lead us to reject H0. Small p-values means small likelihood that the null is true. So here we reject H0 and conclude that there is strong evidence that more than 4% of users suffer from side effects, and so the FDA should put stronger warning labels on this particular medication. Second example. This one is from AAA. AAA claims that 54% of all automobile fatalities are due to driver error. So a researcher reviews 44 fatal accident reports, and of these 21 were due to driver error. So is there strong evidence to contradict this claim? So the claim here is 54%. AAA claims 54% of all fatalities are due to driver error. Now notice here it doesn't ask, do we think it's higher than this, lower than this? It just says, is it true or not? Do we have evidence to contradict this? So something other than 54%. So here this is a two-tailed test. The null hypothesis is 54%. The alternative is not equal to 54. So again, we plug into our test statistic. 21 out of 44 is our p-hat. We plug those numbers in and get negative 0.83. So since this is a two-tailed test, I'm going to take that negative 0.83 and look it up in the z-value, find the probability further out in the tails, so less than negative 0.83, but then I'm going to double it because this is a two-tailed test. I'm considering both tails. So here I get a p-value of 0.4066, which is obviously larger than alpha. This is not a small p-value, so we fail to reject. So we do not have strong evidence to contradict the claim by AAA. So again, remember, when we reject H0, we're making a strong conclusion, a definitive conclusion that we think the alternative hypothesis is true. That's what the data supports. When we fail to reject, what we're saying is we don't have evidence to contradict the claim in the null hypothesis. Here the initial claim was 54%. We don't have strong evidence to say otherwise. That doesn't necessarily mean it's exactly 54%, but our data is sort of in that ballpark. If you take 21 out of 44, you get about 48%. So it's not 54, but it's in the ballpark. So our fail to reject means no, we do not have strong evidence to contradict this claim.